Good evening, class. We were dealing with 5.5, so properties of logs. I hope you've had a chance to go over the properties of logs. These are the stuff we covered. You have to be very comfortable with it to move on. And we looked at this example. I believe everybody remembers and everybody's done well. So let's see if we can practice with a little bit more examples, okay? So those are the ones we did. So here's the next example that we are going to look at, okay, class? So let's see if I can, I want to make sure I have my pen in order. Okay, so we are looking at this example log. The base is not important because you just keep on writing the same base. Is everybody with me? Just keep on writing the same base. We want to decompose this, and I have put the formulas for you here, the properties that you're supposed to know. I want to give everybody a minute, and I want to see what you can come up with as your final answer. Okay, so let's give everybody a moment. All right, so it really shouldn't take that long. When you look at the first one, part A, it's the log of the top over the log of the bottom. And bear in mind, we're going to keep the same base, whatever is given to us. In both cases, the exponent becomes the coefficient. Okay, and you're done. That's all there is to it. You're done. The next one, it's important to use the product rule. So we say that the two is x squared and cube root of square root of x minus 1. And now the second piece, it's important to write it as x minus 1 to the power of 1/3. And now the exponents in both cases become the coefficient. And again, I hope you realize you keep the base, okay? All right. Now, again, a quick minute. Let's see what we can come up with. All right. So the same thing. We look at the top and the bottom. We separate them using the quotient rule. By the way, if you get enough practice, as I mentioned even in intermediate algebra, you can do this in one shot. You really don't have to take too many steps. So ln of the top minus ln of the bottom, and you separate them, okay, as follows. Ln x cubed and ln of square root of x minus 2. Remember, x minus 2 okay, I need to get my pen. It's x minus 2 to the power of 1/2. And so every exponent becomes a coefficient.
I have a quick question.
Yes.
On example B,
Yes.
the result, is it going to be x minus 10 or x minus 1?
Minus 1, my apologies. That is
Okay.
absolutely right. You are absolutely right. I'm glad you caught that. That's fantastic. I really appreciate it. Okay. Yes, indeed. Sometimes, it's just a typo that I have because I've been putting this stuff together. And so that happens. Thanks again. Thank you so much. I'm assuming it is done so we can move on.
Yes.
Perfect. I've made some changes in order of the question so we can go through fairly fast, okay? All right. Oh, in this case, I don't have a proper. Okay, so let's actually, because we don't, let's stick that for now. Okay, class. So this way, you can see the answer, and that's fine, because I don't want to waste time. So let's go over that quickly. All right. Now we want to go the reverse process. We want to put it into a single log. So as you look at the first one, part A, 3 ln 2, 3 becomes the exponent. Okay. And so it ends up being ln of 2 cubed. 2 cubed and x squared can combine into 2 cubed x squared or 8x squared. Okay. So that's the idea behind that. Part B, we can bring the coefficient 1/2 and make it the exponent for 4. We can bring the coefficient -2. We keep the negative sign. We bring the 2 in, becomes 5 squared. Now this is 2. This is 25. So because there is a negative sign in between, it uses the quotient rule. Quotient rule class. Okay, let's move on. Part C. Same thing again. We are, again, by the way, again, I really can't emphasize this enough. All of this can be done really in one shot with enough practice. So right now what we have is -2 becomes the coefficient becomes a exponent, 3 becomes a exponent, and the last one just remains unchanged. We can combine these two because they both have, notice, they both have a plus sign. Therefore, we go with the product of those two. The other one, which has a negative sign, we keep it for now. Okay. And then we use the quotient rule on that. Use the quotient rule on that. Needless to say, 2 cubed is 8. And 3 to the power of -2 is 1/9. And that's why this goes there. Okay. I hope it makes sense to everybody.
Yes.
Any questions? Okay, perfect. We're going to use the change of base formula. Again, I hope everybody remembers it. The idea behind the change of base formula is very simple. What if I want to evaluate a log with a base which is not common, or natural log like base e? Okay, that's the idea behind that. And so what it means is that we can rewrite the log such that the argument is at top, the base is at the bottom with respect to any other, notice, any other base, any base of your choice. For example, you can write log, no base, it's common log, or ln, the base is e. So if you want to approximate those, and I'm sure everybody knows how to do that, there is really nothing to it. The first one, you plug it, you use the formula. Whether you use the common log or natural log, the ratio becomes identical. We are not saying, it's important to know, log 89 is not equal to ln 89. That's not what we are saying. We are saying the ratio is the same. And if you use a calculator with a bunch of decimals, you get to this answer. Okay? Very straightforward, I hope. The next one is the same thing. The same thing, meaning we can use log of square root of 5 over log of 2. Okay? Or you can use ln. It makes no difference. The first one.
Professor?
Yes.
You were fading out there, getting really low and then choppy. Can you please repeat the last thing you said?
I'm very sorry. A little bit louder. I couldn't hear you, please.
The very last thing you were saying, the microphone was fading out and it was chopping up.
Oh, okay. I'm sorry. Are we okay now?
It's better now, yes.
Okay, great. All right. So in this case, we write log of square root of 5 over log of square root of 2 or ln of square root of 5 over ln of square root of 2. Makes no difference. Square root results in 1/2. We drop the 1/2 from the top and the bottom. It simply becomes ln 5 over ln 2. Okay, you can drop the 1/2. Okay, in both cases, you can drop it, okay? I'm writing both just to make a point. It doesn't matter which one you use. And evaluation after a bunch of decimals. This is the approximation. All right. We're going to go over the last page quickly. All right. Write in terms of A, B, and C, where ln2 is given as A, ln3 is given as B, ln5 is given as C. So what happens is that you have to decompose this so that it becomes ultimately involved with 2, 3, and 5. For example, ln of 6 over 5. The bottom is 5, we are in good shape. But the top is not containing 2 and 3, just the way it's given. Is there anything we can do to excuse me, fix the problem? ln of 6 over 5, what would we do? Anyone? Can we decompose 6 somehow? 6 is a product of what numbers? Anyone?
2 and 3.
Can we write 6 as what?
ln2 and ln3.
No, 6 itself is 2 and 3. And then it's ln, the top is 2 times 3 over 5. So it becomes ln of 2 times 3 over 5, or ln2 plus ln3 minus ln5. Perfect. That sounds good to everybody? Makes sense, everybody? Okay, good.
Yes, thank you.
What do you think we can do with part B? Anyone? How do we break this such that we have only 2, 3, 5? Any ideas? Okay. Everybody knows 5 is 5 squared, right? Everybody knows that.
Yeah.
Okay. So ln of 5 to the power of 2/3, which is 2/3 ln of 5, which is 2/3 c. Does that make sense?
Yes.
Okay. Now what I want you to do, class, I want you to take a moment, think about number 24. How do you decompose number 24? So it has only numbers 2, 3, and 5 involved, whatever that you can make it happen. Okay? What comes to mind? In other words, you can factor it. So what do you get? Anyone? Any ideas? We want it to involve only 2 or only 3 or only 5 or a combination of those in some way. What comes to mind? 24.
2 and 3.
Say it again.
2 cubed times 3.
Beautiful. That's what we are looking for. 2 cubed times 3. 2 cubed times 3. So ln of the first one is 3 ln2. or 3a, plus ln of the second one, ln 3, which is b, and you're done. I'm sort of skipping a step. I want to make a point. By now, you should get very comfortable with that. So I want to give everybody a chance to do the next two questions. See if you can do this. You can try it. See if you can do this in one shot, okay? Just give it a shot on your own. See if it can be done in one shot. Not that you have to do it that way. But that's, by now, you have probably enough practice. All right. The first one is ln of the top minus ln of the bottom. And the top has 2 and x, and square root of x squared plus 1, which is the same as x squared plus 1 to the power of 1/2. So I hope you see you're dealing with the complete decomposition here. So a, ln of the top is ln of 2 plus ln x plus 1/2 ln of x squared plus 1. And the bottom, there's not much we can do, minus ln of x plus 3. Second case, how do we factor x squared minus 2? It's x minus 2x plus 2 in any order you like. So it's ln of each piece, you add them up, and minus ln of the bottom. And bear in mind, we should keep the same base, whatever that we are dealing with. We always keep the same base. Sounds good? Any questions?
No.
All right, so we are dealing with logarithmic and exponential equations in this section. So we looked at composite functions. One-to-one functions, inverse functions, exponential functions, logarithmic functions, properties of logs. There's a lot here on this page, class, you need to get comfortable with, okay? So here's the section of interest, exponential and logarithmic functions. All right, let me put that in slide mode. And basically what it is, we are dealing with the following rules. They're very straightforward rules. If you have an equality class, if it involves exponentials, they must have the same base, they must have the same exponent. If you're dealing with logs, the same thing, of course, with the proper restrictions, of course. So that being the case, it means, for example, if you have a to the power of x and a to the power of y, then x and y are equal. That's really the bottom line. So we're going to use that to solve equations. So here's a simple one, 3 to the power of x equals 81. As we notice on the left side, the base is 3. All we have to do in this case, think about 81. Is there any number that has base 3 with some exponent that becomes 81? Anything comes to mind, class? Any number comes to mind? 81
4.
is, say it again?
4.
Excellent. So that means x must be 4. It's that simple, class. Does that make sense?
Yes.
All right. So with that being the case, we do the same thing on part B. The left side has base 4. And we know that 16 is 4 squared. We bring it up, becomes 4 to the power of negative 2. So the two exponents must be the same. And we have the answer for x. Of course, all of this can be checked, but just to give you an idea as far as the process is concerned. 8 to the power of x is 1/2. What can we do here? Any ideas what base we can use?
Two cubed x. No, does that? Can we do that? Can we do like 2 cube x?
I'm very sorry, but it's very hard to hear you. Can you speak
we do-
louder? Unless
it
my
possible-
mic. Okay, go ahead.
Is it possible to do 2 cube x? Like, does that?
That's
that
right.
Or x
You
to 2?
replace the 8 with 2 cubed. You replace the 1/2 with 2 to the power of -1. So when you replace the 8 with 2 cubed, the power rule says 2 to the power of 3 times x. Okay?
But does x remain an exponent or does it remain a product?
Exponent, of course, exponent.
Okay.
That is called the power rule.
Okay, yeah, that makes sense. Thank you.
Sure. A to the power of m to the power of n is a to the power of m times n. Okay. Just fix this. This is hard to see. So anyways, then 3x must be equal to, so this is a to the power of m times n. It's called the power rule. 3x must be equal to -1, and x is -1/3. Very straightforward. All right. I want to give everybody a moment to think about this and what you can come up with such that both sides have the same base. By the way, if we can't come up with that, there is a way around it, but this is a fairly easy question. We should be able to come up with the same base. So what comes to mind?
So 3 cubed times 2x plus 1. And the other one, would that be like... No, that wouldn't work. That'd be, wait, 3 squared.
So we replace the 9 with 3 squared. Good. What about 27?
3 cubed?
You're done. As long as we see this, we are practically done. We use the power rules. We multiply 2 by 2x plus 1 and 3 by x minus 1.
So it just matters that the bases match, the exponents don't have to?
No, in this case, the exponents don't have to. In this case, we can make this happen. Sometimes you may have the same exponent, and therefore the base must be the same.
Okay, thank you.
So because in this case, my pleasure, it's doable that we can make up the same base. It may not be doable all the time, or maybe a case that we have to approach it differently, or perhaps we can make it so that the exponents are the same and then the base, or a base is missing, we are trying to find it. As you can see, in all these cases, the exponent contains x. Does that make sense? So we set 4x plus 2 equal to 3x minus 3, and that's an easy case. X becomes -5. Sounds good, everybody?
Yes.
Yeah.
Yes.
Perfect.
Yes.
We are going to move on. Okay. Okay. All right. How do we approach logarithmic equations? There are two types. One of them is that we have log and nothing else, as you can see here. One of them is that we have logs and numbers. When we have logs and nothing else, we don't move anything around. We don't have to, although sometimes it's helpful. We just write both sides as a single log and we move on. If we have logs and numbers, we bring all the logs together, all the numbers together, we put the logs as a single log, and then we go to the exponential format. We'll see that in a moment. For now, as you can see, the left side can use the product rule. Agreed? Now what's happening? They have the same base, namely 5. So they must have the same argument. So in that case, these two arguments must be identical. It's a simple case. I wouldn't worry about that. I assume everybody can solve the simple equation. And the answer is x equals 11. So what was the case here? Logs and nothing else.
Professor, what if they have a different base? Is there a way for us
You
not
can,
to...
no, I mean, there is a way, but we're not going to do those examples. I'm glad you brought that up. They must have the same base. Okay? They must have the same base. All right. Here's the next one. Now, as you notice, one side is a log, one side is a number. By the way, even if on the left side we had more than one logs, the process would be just to put it into a single log. So that makes no difference. I want you to know that, okay? The process is the same. So now what do? Well, we want to put it into a single log. It's already a single log. We don't have to do anything. All we have to do, rewrite this exponentially. How would you rewrite this, class? Can anybody tell us? In an exponential form, how would you rewrite it?
2 to the third power equals x minus 4.
Perfect. You're done. That's it. That's it. If you can see that, I can't imagine anyone not being able to finish it. 2 cubed is 8, move the negative 4, and you're done. 2 cubed is 8, move the negative 4, make it positive, and 8 is 12. It's that simple. We are done. So what I want you to do, look at part C. If you can figure it out, more power to you. If you cannot, look at the properties in blue in the middle of the page. See if that can help you. And so what is the answer? In other words, part C is equal to 4 times what? All I'm asking is, okay, what is this, everybody? That's all I'm asking.
4 times 1 times 2, 8.
One more time.
4, 1, 2 equals 8.
4, 1, 2.
Isn't
Now,
10
what
log
is,
equal?
okay, what is the expression 10 to the power of log 2 equal to, class?
It's equal to 2.
Beautiful.
Equals, but doesn't 10 log equal 1?
We use the fact that logarithmic functions and exponential functions undo each other. I suggest you guys get very comfortable with those properties very soon, okay? Now, this property for common log is 10 to the power of log x equals x. It has got to do with truly understanding the properties and getting comfortable with them. There is no way around this. And as a pre-calculus students, you really should be comfortable with it because you have seen it in both intermediate algebra as well as college algebra. I'm going to move on. All right, we want to solve this. So this is slightly different than what we have seen. So it's 5 times 2 to the power of x. Remember, we want to get to x. So first, let's get rid of number 5. Now we want to try to make both sides having the same base because the exponent is missing. But there is absolutely no way. When that happens, how do we approach that? That's what I want to go over. Then we have no choice in order to get to the x, but take a log. I can take a natural log of both sides or common log. Makes no difference, okay, class? It's your choice. If I take the natural log of both sides, can you tell me the next step? What happens, in other words, to the left side? Anybody?
X ln 2 or x log 2?
Beautiful. X ln 2 or x log 2, perfect. Now the right side, you really have two choices. You can leave it as ln of 3 over 5, or you can change it to ln 3 minus ln 5. It is your choice, class. So what is x equal to? I want you to know this is the precise answer, exact. And we could rewrite it as, okay, let me, x equals just the way it is, or ln 3 minus ln 5 over ln 2. So if the question is come up with the exact answer, you're done. Exact. If the question is a rough estimate with a bunch of decimals, that's your answer. Sounds good. Is there any questions, class?
Can you leave that up for a second? Just
Of
for 1
course.
second. Thank you.
Everybody okay with this class?
Yes.
I
Yes,
hope
thank
it
you.
makes sense to everybody, so I'm going to repeat. If we can't come up with the same base in order to get to the exponent, we have to undo the exponent. How do you undo the exponent? You take a log. Which log? Your choice. Common log or natural log makes no difference. Are we ready for the next one, class?
Yes.
Perfect. All right. Now, this one is a different type of question, okay? Again, I want you to be exposed to all kinds of questions. When you come across this, this ultimately becomes a quadratic function. And that has got to do with practice. If you have enough practice, you can see that. When you look at 9 to the power of x, if you replace that with 3 to the power of x, how does it work? 9 is replaced with 3 squared. So it's 3 squared to the second power, okay? Or 3 to the power of x to the second power. I want to make sure everybody understands what's going on. So 9 is equal to 3 squared. 9 to the power of x is 3 squared to the power of x. It's equal to 3. I don't know why it does that. 3 to the power of 2x. Or you can say 3 to the power of x squared. All of them mean the same thing. Why are we writing it in this form? Now we can let 3 to the power of x be a variable of your choice, such as u or y, or choose anything you want, except x, except x. And now this is a simple case of factoring. And there are two answers. U is either 3 or negative 2. Okay, so what happens? We are going to replace the u. to find out what x is. Is everybody okay up to here? Class?
Yes.
Okay.
So what happens to the first one? The first one says x must be what? X must be 1. X must be 1. And what about the second one? 3 to the power of x must be positive. As you hopefully remember, the range of exponential functions a to the power of x is from 0 to infinity. Domain is from negative to positive infinity. So it has to be positive. If you have any negative answer, is out. Sounds good? Is there any questions? We're going to go to the next example, okay? All right. Now, in this case, part A, we are dealing with a bunch of logs and some number. And what do you think we should do as our first step, everybody? Anyone can tell us what's our first step? I went over that. I said, if we have an equation that it has a bunch of logs and numbers, what do?
Do we put the logs on the same side?
Very good. That's the first step. So we bring the logs to the same side. What is our next step? We simplify the log into a single log. So we use, in this case, because of the plus sign, we need a product rule. Now, one side is a log, one side is a number. What's our next step? Anyone?
X squared minus 7x.
When you have a log and a number, what do? You put it in what format? Exponential format, class, which is 2 cubed equals x times x minus 7. Okay? All right. Now you get x squared minus 7. X equals 8. You move the 8 to the left. Okay? And you factor it. Gives you two answers, 8, -1. Are we done here, class?
No.
No, you have
No.
to solve for,
Positive?
One more time. I heard something good.
oh, you have to solve for x.
We have already solved for x. X is either 8 or -1.
It has to be positive.
Has to be positive. Okay, I want to make sure everybody understands what's going on. All you have to do, go to the original equation. Original equation, nothing in between. If you look at the first one, that says x can't be -1. You don't even have to look at the next one. Okay, sounds good? However, there may be something that, there is nothing wrong with the negative number. It can't make the argument 0 or negative. And I want to explain that in case instead of x, let's say we had x plus 2. -1 can't make it negative. Instead of x minus 7, let's say we had x plus 7. The -1 can't make that one negative or 0 either. So -1 is fine. So it's important to know it's not negative numbers we want to get rid of. Okay? We cannot have negative arguments. Okay?
Professor, I have a question about
Yes.
A. How did you get from log 2x times x minus 7 equals 3? How did you get an 8 in the next line right below that?
From the 2
Okay.
squared.
First of all, you okay with this one, right?
Yeah, yeah.
So from here, I went to here.
Oh,
And then here, right?
okay.
By definition of exponential, the argument is 2 cubed. X times x minus 7 is 2 cubed. Do we see that?
All right, when I was following,
Everyone?
I put equal 3 in mine. I put it wrong. That's why. Okay, I understand.
Is this okay?
Yeah, it makes sense.
Okay.
'Cause
All
I
right.
put on the 3, and I think another
No
class.
worries, no worries. Now that you've seen part A, let's give everybody a chance to work on part B and finish it up. So let's see how we can come up with the answer. All right, class, what's our first step?
Send the logs to one side.
Absolutely. Second,
Bring the logs together into one line. So you
perfect.
have
What
log.
do we get? Log base 2 of what?
X
Since it's
divided
a
by X
minus,
minus
it's
7.
x over x minus 7.
Perfect. You're practically done. Now your next step is just like the previous example. The argument of log is equal to 2 cubed, which is 8. And you solve this by the cross product. I want to make sure everybody understands what we mean by that. You can write 8 as 8 over 1. So 1 times x. 8 times x minus 7. That's a very simple case. Okay. So 8 times x is 8x minus 56. And then we move the x to the right. That becomes negative. So 7x is 56. Divide by 7 and the answer is 8. I put the two questions side by side. I hope everybody can pay attention to that and see why I did that. So you can see the relationship between the two. One becomes a product rule and what becomes a quotient rule. Other than that, it's not a big deal. Sounds good, everybody?
Yes.
Any questions?
No.
Perfect. All right, class, we are moving on towards the application. And so financial models. Again, the composite function, one-to-one functions, exponential functions, logarithmic functions, properties of logs, and exponential and logarithmic equations. So let's go to financial model. Uh, everybody can hear me, class?
Yes.
Yes.
Excellent. All right, let's start with basics. Everything that before, I just want to make sure that you're comfortable with that. So let's quick over the synopsis of what's coming. Simple interest, everybody remember R equals PRT. What P, the principal, R is the rate, T is time. Compound interest, okay. So the second one, compound interest, class. Okay. A equals P times 1 plus R n to the power of nt, compounded n times per year. Now, for example, when we say annually, n equals 1. Semi-annually is 2, quarterly is 4, monthly is 12. So we know what's n. If this takes place continuously,
Professor,
non-stop,
we can't hear
yes,
you.
You keep breaking.
You keep
okay,
breaking and the screen is getting blurry.
it's internet connection. Well, I'm supposed to have a gig blast. I don't know if you've heard of that, but either it's because of the situation nowadays or I never got it. It's just a false advertisement. One, I know. Can you hear me, everybody?
Right now, yes, but you were cutting.
Okay, I'm sorry. So quickly, simple interest I equals PRT equals P times 1 plus R over N to the power of N compound interest. In the case of a compounding, N represents the number of compounding. If its N is 1, semi-annual is 2, monthly is 12, and so forth. If it's continuously, it's P e to the power of RT. Now, what I want to explain here is that really depending on the text that you're using, they may use different formulas. If you look at the first one, class, A equals P e to the power of RT. The second one, P equals P sub 0 e to the power of KT. K is the same as R. In this case, PC sub 0 is the same as P and the same as A. The reason I mention it, it really depends on the text. So when K is K or R, okay, K or R, okay, where P is the initial starting value of the quantity, if you look at the very first one. And K or R is the constant growth rate or decay rate. Depends on whether K is positive or negative, okay? And as you can see, this exponential growth is very straightforward. We've seen it before, it's not a big deal. So sticking with that, with the growth, we have what's called doubling time. What do we mean by doubling time? How long does it take for the original size or original investment P sub 0 to get to 2 times that? That's called doubling time, okay? So with that being the case, everybody, we are refreshing everyone's memory about doubling. On the other hand, if you're dealing with a decay, we have a half-life, the amount of time takes for an amount of radioactive substance to go to half of its size. So with that, we can calculate the doubling time. So if we put 2 P sub 0 equals P sub 0 e to the power of KT, we can cross out the P sub 0 from both sides, becomes 2 e to the power of KT, and taking a natural log from both sides gives us ln2, and ln of e to the power of KT, which is KT, and therefore T is ln2 over K, or K is ln2 over t, where t is the doubling time. Okay, class? All right, we want to look at the proof of compound interest quickly. I is PRT, okay? If we take time to be 1 over n, becomes PR times 1 over n, or P times R over n. So the next time we look at the amount is the combination of the principal and the interest. We add them up, we factor out the P. And after the second compounding, we have a new principal, okay, that we got before, and the interest on a new principal. What was the new principal? Okay, this one. Okay, and we are going to multiply it by R over N again. So when we do the factoring, okay, we get R over N to the second power. If we continue with the process, we end up with this formula. Of course, I don't expect you to prove that, but this is the synopsis of how we arrive at it, and it's completely posted. What we are interested in, can we just use it in case the question is given? So, and of course, many times in this course, we're interested in compounding continuously. As we look at this example, okay, we notice that we want to find the amount that results from investing principal P of $2,000, an annual rate of 8% compounded continuously, okay, continuously. And that's really the key. So all you have to do, plug it into the formula. I put both formulas at top in blue, okay? The reason I did, because they're identical. It depends on the course that you're using and the variable that is being used, or the text. They mean the same thing. So it's a simple case of plugging in and coming up with the answer. Okay, so 2000 is the principal and 0.08 is the rate. .08, okay. We've seen sort of the proof for this one, so I'm going to quickly show you what we have seen before. You can look at it on your own time to see how it's done. This is the compound interest. The way we looked at compounding continuously, we just rewrote R over N as 1 over N over R, okay? And so K becomes N over R if you let K represent N over R. So K is representing the denominator. And so N becomes KR. So what that means is, now you are going to replace the N over R with this, and you're going to replace this N with this value. And so basically, this is T, by the way, class. This one is T. And so you get P1 plus 1 over K to the power of K to the power of RT. And that is the definition of E. I think we mentioned it at some point. And we look at the proof. This is the way we proved it in college algebra. We look at a more, detailed proof using calculus later. The next thing I want to look at is the idea of effective rate. So I want to explain what's an effective rate. Effective rate, ultimately, it means the interest that happens in really 1 year, okay, if you take it to be a simple interest, okay? So in this example, for example, it's going to get compounded continuously. Okay, so we know the formula A equals P times 1 plus R over N to the power of NT, and you replace it accordingly because N times T is equal to 1. So in 1 year, I want you to know why in this formula we don't see a T. It's N times T. Okay, so we should really add T equals 1. Okay, so we plug into calculator, we end up with a number. So the interest is what's at top of $1,000. Okay, so that's the interest. That makes sense? So with that being the case, if we go with I equals PRT, and again using the same T, namely T equals 1, the amount of interest is $30.42. Okay, and remember, P hasn't changed. P is still 1,000. So that means we made $30.42, which corresponds to the following rate. So, to recap, if we were to receive a simple interest, the rate would be 3.042. That is called the effective rate. So one more time, I want to make sure we understand the concept. What is the effective rate? What if we didn't do the compounding? That's it. What if it were just a simple interest? The amount of interest, okay, can be divided by the principal, and that becomes your rate. That is the effective rate. So with that being the case, let's see how we calculate it in different cases. This is a compound interest. P equals 1, A equals P times 1 plus R over N to the power of NT. And this is compounded continuously, okay? All right. And so in 1 year, class, here's what happens. When we look at the amount, it's important to see the amount is this with you when we use the simple interest. The simple interest gets added to the principal and it gives us this formula. So what do? We set both equations at the bottom equal to this formula. Okay, let me use a different color. We set it equal to this formula because when T equals 1, okay, that R that you see, okay, P times 1 plus R times 1, that R is called R effective or R sub E. So with that being the case, if we set them equal, okay, so remember, we are going to set them equal. What happens that the P cancels out, okay, so we are setting the right sides equal. The P cancel out and R effective becomes, so I want you to set this one equal to this one and you see the answer. I want you to try it later on at home. I want you to set, let me use a different color. I want you to set this one also equal to this one. By that, I mean the right side. The P drops and you see R effective is E to the power of R minus 1. So for now, we're going to use those. And I suggest you try that. It takes a second to finish the job. Here's a simple example that can put this to a good use. Okay, what if we have the following situation? We want to open a money market account and bank A gives us 4% annual interest compounded daily. B gives us 4.1% monthly compounded, and C offers 3.95% compounded continuously. Determine which one is giving us the best deal. In which case, you really have no choice but to calculate the R effective. The one with the larger R effective is the one you're going to go with. And we showed the way we calculate R effective in the previous page. So for bank A, we replace the R with 4%. Okay, class, 4%. Okay. And because it's daily, normally they use 365 in banking. I want you to know that, although one day is 365 days and normally 6 hours, but 365. So now you use a calculator, okay? If you want to write it as a percent, becomes that. With bank B, here's the formula, because you're going to use 4.1% here, and monthly means 12. There are 12 months. Now you put it into a calculator, class, okay? I don't want to waste time on that, but you get the picture, I hope. Now, the last one says it's going to be done. Let me use a different color. It's going to be done continuously. So we use this formula. So e to the power of 0.0395 minus 1. And we end up with that, which is 4.029. Obviously, which one is the largest? That would be our answer. Okay, sounds good. So the answer would be bank B. All right. Here's the next one, class. If we are given A equals P times 1 plus R over N to the power of NT as the equation for the compound interest, and A equals P e to the power of RT for compounded continuously, we can solve for P. Class, we can solve for P. All we have to do, move this one to the other side, move this one to the other side. How do we move it to the other side? We divide by it. Division means negative exponent, class. Oh, I'm sorry, it's the order is wrong, but that's fine. The order of animation is wrong. In any event, let's see what we have now. Okay, never mind that. All right, basically, why don't I write it here for you? This one becomes, let's go with, this one becomes P equals A divided by what I mentioned. Division means what? Negative exponent. This one gives you A e to the, okay, so you're dividing by e to the power of. So using that for the first one, when we have 10 years, that's the time. Okay. Bond can be reduced. Okay, let's see, 10 years for $1,000. How much should you be willing to pay? That would be your A. Okay. So 7% is the rate here. Compounded monthly means 12. And you plug in, you have the answer. The other one uses the second formula. You plug in, you get this one, okay? I hope that sounds good. Okay, and of course, now I think we have those formulas. The order in animation is wrong. So anyways, we are going to go to the next example, if it's okay with everybody. Everybody following this, right, class? Everybody can hear me?
Just write it
Perfect.
down.
All right. We've already looked at the concept of doubling, okay? So how long will it take for an investment to double in value if it earns 6% compounded continuously? So let's actually go over the proof one more time, okay? You can do it. We've gone over the proof and we showed that T is ln2 over K. I hope you remember that. And you can use that class, okay? Remember, this is your R or K, okay? Now, look at the way we do it. If we go with this formula A, now, do you have to put 0.06? You can keep it as KT or RT and then at the end plug it in, okay? But if you put it in, so you drop the P, you take a natural log of both sides, and in order to find the T, the left side is ln T, the right side becomes 0.060, and you divide by 0.06, you have the answer. You could, as I mentioned, you could simply put, as we did that, 2P equals P e to the power of RT, okay? And so you drop the P to e to the power of RT, okay? And you take a natural log of both sides. ln2 is ln of e to the power of RT, which is simply RT. And so you want T is ln2 divided by R, you divide it by 0.06. So that's one way to do it. If we wanted to triple, we can do the same thing. Use the 0.06 or just keep it and use it at the end. You can go with E equals e to the power of RT. I hope you see that the left side now becomes 3 times P. Now, again, the same thing, you go through the process, you drop the P, you take a natural log of both sides. The right side becomes 0.060, you divide by, and that becomes ln3 over 0.06 precisely, and roughly 18.31. And again, this is the formula that was discussed. By the way, notice K or R, we're going to use this back and forth because they mean the same thing. All right. I hope everybody's okay with this stuff. We've seen them before, so it's really is not a big deal, I hope. All right. Here's the next one, class. In an account that if an account pays 8% annual interest, compounded continuously, and that's really the key, paying attention to the format. How long will it take for a deposit of 25K to give us 100K? Okay. All right. So basically, you can go through the process and put 100K as A. So again, I want to make sure we understand this is A, this is P, and this is R or K. So you can plug it into a formula and solve it. So A equals P e to the power of RT. A over P is e to the power of RT. I want to show you this for one reason and one reason only. The time is ln of A over P divided by R in general, if we want to go through that process. Why am I putting this up? I want to make sure everybody understands why I'm putting this up. If somebody asks you, given this equation, how do you solve for T then you end up with that, okay? That's the idea. Needless to say, ln of a over p is the same as ln a minus ln. This is in case one. And so t is ln a over ln p. So in this example, this is the given, and t is missing. Now you have a choice, okay? Let me just start with, the choice is you can say 100,000 equals what? 25,000 e to the power of, what was the rate? 0.08t, and finish the job. I hope you realize you have 4 on the left side, and go through the process. Or the formula we just came up with, t is ln of a over p. This is 4, and you come up with the answer. Okay, so it takes approximately that much, that long. Or if you go with this one, so you have 4 e to the power of 0.08t. And so if you take the natural log of both sides, you have 0.08t. You're taking the natural log of both sides. And then from here, you can find the t. Hi, class. We're going to continue on that thoughts, dealing with exponential compounding, if you will, which is essentially exponential growth. So in this section, exponential growth and decays of interest to us, mainly. And so, again, the synopsis of what we covered. And it's important to remember this one because we're going to continue with this model, if you will. So we discussed the doubling, okay, class? Now, if we continue on that thoughts, when you're looking at an exponential model, okay, the exponential growth is a of t equals a sub 0 e to the power of kt. And please understand that, you know, in this case, of course, we don't have, this is the same as exponential functions. You see, this we don't have on the left side because it's the time sensitive. Time must be positive or 0. And that's why we don't have that. But if you extend both, you see the basic function of exponential functions that you have seen, okay? So this is called equation of a population that obey the law of uninhibited growth. There is nothing stopping it. Normally, that's not the case. I want you to know that in real life, we don't have a uninhibited growth when it comes to a population. There are other, things that can stop it. And for example, the limitation on food and resources. And that's why we use something called like logistic growth. So with that being the case, let's look at this one now. If P0 is invested once and for t years at interest K, again, remember this is the same as R. Compounded continuously, we use this formula, which is ultimately the same as this one. And I want you to know these two really are the same. We're just using different variables. If we go with that, P sub 0 is called the present value, okay? And P of t, what we end up with, or A, if we put it on the left side, is the future value. And so A of t is A sub 0 e to the power of kt, or P of t is P sub 0 e to the power of kt. or p sub 0 e to the power of rt. I'm writing all of them. Again, I can't emphasize the importance of understanding k. R makes no difference, class. Okay, it's just depends on the text. So we have proved the doubling. Everybody knows that. We've gone over that. Now, if you have an exponential decay, it can be shown that then ln of 1/2 over 2 divided by t is the k that we use for half-life. All right, let's look at this simple example, class. Okay, so can somebody be kind enough to read the question? I'm sure you're tired of my voice. I know I am.
Colony of bacteria grows accordingly to the law of uninhibited growth according to the function n to the t equals 90e point to the 0.05 to t, where n is the number of cells and t is measured in days.
Thank you so much. So when we look at this, what is the initial value, class? Anybody? What would be the initial value in this case?
0 times equals 0? No?
Well, no. Did I hear 0? No, remember, one way to write this is n of t equals n sub 0 e to the power of, I don't know, kt, let's say. So n sub 0 is simply 90. Now understand, you don't have to calculate that. All you have to say it's 90 and it's okay with me. But what I want you to realize, initial value refers to time being 0. So when you replace the time with 0, we call it n sub 0. And obviously this is e to the power of 0, which is 1. So whether you go through the process or not, I put the process for you for a simple reason. Why do we call this initial value? Because it happens at t equals 0. Sounds good? Now, the growth rate refers to k or r. And everybody can see from the equation, it's 0.05. Can we see that, everybody?
Yes.
So the purpose of those two questions is recognition of the given. Okay, the initial value and the growth rate. Okay, the growth rate is the k or r. Okay, basically k or r. And that happened to be 0.05 or 5%. Okay. So, and n is the number of cells, and t is measured in what? Days. Therefore, what is the population after 5 days? Just replace the t with 5, everybody. N of 5 is 90 times e to the power of 0.05 times 5 becomes 0.25. You raise e to the power of 0.25. You multiply it by 90. You rounded accordingly, class. Okay? How do we round it? We want to look at the number of bacteria, okay? Therefore, we write it as a whole number, okay? So if for the sake of argument it's 115.7, we change it to 116, or if it's 116.4, we change it to the same. So you round it accordingly, okay, to the nearest whole number, just because we are interested in the population. All right. When will it reach 140? That means n of t is 140. So you replace it. Let's give everybody a moment. See if you can figure this out, and we move on. It's a simple case of solving an exponential or logarithmic equation, if you will. So let's give everybody a moment. So obviously we get rid of 90, that means we divide by it. We take a natural log of both sides. Natural log of 14/9 equals 0.05t. We divide by 0.05, and then we write it with a bunch of decimals. Remember, this is talking about time, so you don't have to put it as a whole number. So 8.8, or maybe more decimals, it doesn't matter, 8.8 days. Now, finally, the doubling time. You can use the formula here. Or you can go through the process. ln2 divided by k, which is 0.05. Because we have worked it out, we can use it. If we haven't proved that, it's a different story. Or you can go through the process, okay? So, if you go through the process, doubling means 90 becomes 180, divided by 90 is 2, and t is ln2 divided by 0.05. Do you have to do this? No, you can use the formula because we developed the formula for doubling time. K equals ln2, okay, divided by R or K. All right, sounds good, everybody?
Yeah.
Excellent. I hope everybody is comfortable with this and it's coming back to us. We've seen it before, okay, class? So it should be fairly obvious what we need to do from. We've seen similar questions even in intermediate algebra. All right, let's see. Now in this case, a colony of bacteria increases according to the law of uninhibited growth. That means using this formula. Okay, or A equals PE to the power of RT. However you want to put that, it's not a big deal. So if N represents the number of cells and doubles in 5 hours, and T is the time in hours, express N as a function of T. First of all, this is the general formula that you see at the top anyways, okay? And the reason we are using that because it says uninhibited growth, okay? Now, what we can do again, we can use this formula. And remember, doubling takes place in 5 days. So you replace the T with, 5 hours. And that's it. That's simple. Or again, so you are exposed to it again, just for practice, you can go find that. 2n sub 0 is n sub 0 e to the power of k times 5. Drop the n sub 0, take a natural log, divide by 5. And this is exactly what I mentioned in the first place right here. So you don't have to go through the process simply because you've done this before. Okay, class? Sounds good? Now, if there are 10,000 cells initially, remember initially for part A, we didn't know that and we used the general format. Do you see that? Now, if it's 10,000, how long does it take for them to be 25K? We've looked at a similar question and we could use that formula, but if we want to develop the formula, we replace the left side with 25,000 and we replace the n sub 0 with 10,000, okay? By the way, we got this formula, okay, class, as a result. So What is n of t? Okay, is 25k. What is n sub 0 is 10k. Okay. And so we replace them accordingly. By the way, I want you to pay attention. This is not, this is ln2 over 5 class, okay, not ln2 over ln5. Let me just make a point here. I want to make sure everybody understands what we mean by that. Number one, this is not ln5, this is 5. Let me tell you why I put that. I want to make sure everybody understands. It's a good practice to put the precise answer. Notice I used tons of decimals. When you do the calculation, and especially for example, I suggest you stick with ln2 divided by 5 when you plug it into your calculator for the next step. That gives you a better answer, a more precise answer, class, rather than a decimal representation. So if you use ln2 over 5, okay, not ln5, you drop the 10,000 and you divide by it, you get 2.5 or 5 halves. So if you divide by 10,000, it results in 2.5 or 5 halves, okay? And notice over here is correct, okay, class, this is ln2 divided by 5. Okay, it's not ln of 2/5. ln2 is a number divided by 5, okay? And so let's take a natural log of both sides. Left side becomes ln of 5 halves. Right side becomes the exponent, just the exponent. Now, what is the exponent? ln2 divided by 5. And I want you to realize the difference between these two, okay? So you divide by ln of 2 over 5. And notice the way I write it here because I want to make sure it's not confusing, okay? So this is really ln of 2 divided by 5, okay, everybody? ln of 2 divided by 5. And this is precise, and then you answer it with some decimals, okay, class? All right. We want to go to the next question. Is everybody following what's going on here?
Yes.
Okay, great. So again, maybe this step, just quickly, we can write it as ln of 5 halves is ln2 divided by 5t. That may be a better way to understand this, okay? Which results in ln of 5 halves over ln of 2 divided by 5, which that number 5 comes up. By the way, this one, just again, this is the same as writing 5 ln of 5 halves over ln2, because it's a complex fraction. The 5 in the denominator comes up, and that gives you the answer. Okay, class? All right. Now, in the case of a decay, we are dealing with an exponential decay and the concept of a half-life. The concept of a half-life refers to the fact that what happens, okay, is also ln of 1/2. What happens when the initial amount goes down to half of its original size, okay? So It says, how old is this? A bone is found to have 45% of the original amount of carbon-14 if the half-life is 5,600. How old is the bone? So what I want you to realize is carbon-14 is a radioactive substance. Okay, that's why they deal with what's called carbon dating, and they can date it by looking at and measuring the amount left in that substance compared to what it's supposed to be. Okay, and again, another thing that I want to add: when you have this one class, also you have the K. K is ln of 1/2 over T, where T is the half-life. All right. So when I say that, it really depends on the format that you write it. So let's look at this. If we stick with a positive K here, just the way it is given, okay? And we go through the process. Now, you don't even have to go with 5,600. You can keep it as T if you want and calculate the T, okay? You drop A sub 0, okay? And so if you keep it as T, you can say 1/2 is E to the power of KT. KT. Okay. Now you take the natural log of both sides. So when you take the natural log of left, you get ln of 1/2. The right side, the exponent comes out. So in this case becomes ln of 1/2. And the right side is left with the exponent only. And this gives us this formula, everybody. Okay? Is everybody following that? Maybe I put it like this. So whether you use this formula or you go through the process, it's fine. So ln of 1/2 divided by 5,600 is the answer. You can even keep it as ln of 1/2. Now, it's important, if you want to keep it that way, class, please understand, let me use a different color. If you want to keep it like that, please understand K is the same as negative ln2. Why does it do that? Minus ln2 over 5,600. Can anybody tell us why I wrote minus ln2 instead of ln of 1/2? Anybody? Why did I change ln of 1/2? Go ahead.
Because you put the negative?
Negative.
No. Why did I write instead of ln of 1/2 as minus ln2?
Same as to the -1. So log -1, ln negative ln1.
There are two ways to look at it. Yes, you can write it as 2 to the power of -1, and it becomes minus ln2, or you can write it as ln1 minus ln2, and ln1 is 0. Both ways are fine. So you can think of it as,
So
let me write it here.
It.
The top is ln1 minus ln2. This is 0. It's minus ln2. All right. You can use that as a precise answer, and you move on. You don't change the ln2 until, you know, when you plug in. Or you can change it to -0 point with a bunch of zeros and 124. By the way, these are all approximation. I want you to know that these are all approximation. In some cases, they call this, they say it's 5,700 years. Okay, so I don't want anybody to be confused that it has to be 5,600. So A of t becomes A sub 0, e to the power of -0.000124 t, or as I mentioned, you can say minus ln2 over 5,600 t. So, or okay, minus ln 2 over 5600 times t. All right, so now we have something which with 45% of the original. We don't need to know what's the original. The original is a sub 0. So 45% is 0.45 times the original. So a sub 0 drops. And now you have to do the same thing. You have to take a log. And again, don't forget, the reason we take a natural log because the base on the right side is e. So we take the natural log, left side becomes ln of 0.45, and the right side is simply the exponent. Dividing by this value, negative 0.000124. And by the way, ln of 0.45 is negative because 0.45 is between 0 and 1. Negative over negative makes it positive. You have an approximation of 6,451 years. Okay, class? Sounds good?